All right, Internet. We are back with Mark Voids a Warranty. How's everybody doing today? I know it's been a week, it's been a long time since I voided a warranty. And in all that time, I've gotten lots of questions. People saying, Mark, you're so great. You void so many warranties, but you've got all these great tools. How do I get started? Well, the good news is all you really need to start voiding warranties is a hammer. Yep, look at this little brass beauty right here, 2-pound sledge. That's really all you need to get started. Now, if you can't afford that, well, just go out to the garden. Find a nice rock. I prefer smooth river stone, but you use what tools you have available to you. So, we've got some decisions to make today. We need to figure out what it is that we're going to take apart. And for anybody out there in TV land that's listening, you get to help decide. Is it going to be this old school? This is a wireless camera somewhere down in here. A couple power supplies. Oh, is that it? Yeah. So we've got a little RF transmitting wireless camera and receiver from, I don't know, circa 90s. We've got a machine vision camera by Teledyne Dulce. I've also got a couple Keyence ones sitting over there, waiting for a future episode. An Amazon Prime Day deal, which is a scale that you can use to reorder things as they start getting empty. And we've got this HDMI display that is delaminating. You can kind of see it happening up here and down at the bottom. So, anybody out there, anybody watching, if you want to vote, just type it in the chat now and we'll get going. Now, while I give you guys a few seconds to vote, I did want to share something with you that I think is kind of cool, and that is what I use to store my tools. Some of you engineers out there might find it useful. And all it is a piece of aluminum rectangular tubing with holes drilled in it and a plate on the bottom. Right? You just drill a bunch of holes and you just drop the tools right in. And to let you see what that looks like from a side view, so you can make that on a drill press. I got the rectangular aluminum tubing at the scrapyard. And I've got one of these for pliers, for screwdrivers, all sorts of fun stuff. You, of course, don't need to do that. It's just something that you might find interesting. All right, time's up. Do we have any votes? Okay, then I'm just going to go for it. We are going to go for this HDMI, who's it by Magedock, and the darn thing has started to delaminate. So, I really don't have a use for it at that point. Displays are relatively inexpensive. The thing I did like about this before that happened was that it had the standard VESA mount pattern on the back of it, and the thing is just so darn thin. But what are you going to do? Once that starts happening, it just becomes a nuisance more than anything else. And I've already since replaced it. So let's get going. On the back side, we've got some tiny screws, undoubtedly metric, that we're just going to go around and pop. These are somewhere in the neighborhood of in the M2 range. Oh, maybe even smaller than that. And they're just located around the perimeter. Don't know what to tell you, Magedock. Talk to your adhesive supplier. And as we get into this, we're going to see if we can't figure out if this is a has any useful parts. I usually like taking these side-lit LED panels apart and getting the stuff that's inside of them, the diffraction gratings. Every now and again you get a loose, it's not too often, but sometimes you get a loose or loose enough polarizing filter. Okay, I'm feeling some resistance already. I assumed at this point this thing would just pop out, but not so much. So all I'm doing is just, oh, I think we know why now. It seems that when I started smacking things, some buttons fell off. So we'll remove those. And now we are free. Okay. This is actually a pretty reasonably built device. All aluminum case. We've got on the back a couple of speakers that are, can't tell if that's hot glue or epoxy, but it pops right off. This is an aluminum, a milled aluminum case. So this thing was put together well enough. It just seems like they had a bad material supplier. I mean, it was still working. We've got a few recesses that were milled out for the for some components on the boards over there, and a couple slots milled in the back for the speaker holes. That grill is, I mean, there's a bunch of foam there, but it's just covering two very small holes, much bigger than it needs to be. I don't know if I can show that to you. Let me just tear through this netting. So see, they've milled out the holes for the speakers, and then they covered the whole area with that grill stuff. And inside we've got a LCD control board. So this looks like a power HDMI audio in, and then we've got a USB touch controller and a key in. That's all those little aluminum buttons that fell off earlier. You know, so we can take a look at that in just a moment. And the LCD, the USB touch controller seems to be these connectors here potentially. So we'll take a look at all of that. And then we're connected to the display itself with a FFC cable, flat flexible cable. And we've got some interesting stuff to look at as we go over here. So let's take a look, shall we? How's everybody out there in TV land doing today? You guys getting ready for the 4th? I usually spend mine running a Firewatch net on one of our local repeaters, just because we're in such a high fire zone. I know, super exciting. But it seems like at least every other year some schmutz comes up into the wilderness and with fireworks and starts a fire. I don't know. Okay, let me get a tighter overhead view for you, and we'll start removing connectors. So this is our main control board. I've already disconnected the speakers. I hope you don't mind. That one's not all that exciting. This is the FFC that goes to our display. And Well, I didn't quite mean to break that, but what are you going to do? Actually, I don't even feel, well, I guess I did just get on it a little too hard. But this, once you remove the connector, those things are designed to have, you know, almost zero insertion force. So they're designed to come out, you know, pretty easily. But that, I mean, I just smashed that. What are you going to do? Up top, we'll try to be a little gentler. Let me push on it with something small here. Wow, yeah, no, that, I'm barely touching that. It's just really easy to over torque. So I was just too rough, and I was almost too rough when I was trying to be gentle. Okay, there we go. So this is our first board removed. I like that. Designed by Kevin. You got to sign your work. Good for you, Kevin. That's pretty good stuff. So we'll get into this board here in just a moment. I'm just kind of looking to see if anything jumps out at me right now. There's some design practices I like, some interesting things. Looks like we've got some solder, possibly some solder thieving pads. And connections for a battery. And this is by Arduino. It's a company I've run into before. So, all right, Kevin. Well, thank you for signing your work. We will take a look at your board and offer tips, tricks, and critiques. And based on the looks of it, I think we're going to be learning from that board more so than we are going to be critiquing it. But you never know. All right. Here we've got our switch. Tiny little bits of tape are keeping everything where they want it to be. I assume it also keeps a little bit of noise down, people hearing things rattling inside. Really is a shame about the glue on this board. All right, let's see if I can be somewhat careful here in removing. Is this taped? Oh, it might be. All right, then, let us see if, do I have a blade handy to sever that? I do. I wonder if that can be my excuse for breaking through that other one. So they had a little piece of tape hiding there. Tricky, tricky. And we've got a full button array there. And then we'll continue our path of destruction. Man, such a nice, solid screen. Only to fail because of either bad glue or bad application of glue. That is such a shame. And sometimes things go bad sitting on shelves. Sometimes suppliers lie to you. I mean, there's a lot of different reasons that things can go south on you. Sometimes it's a situation of being pound wise and penny foolish. You know, you'll spend all this money on, you know, a nice solid aluminum case, nice boards, nice everything. And then when it comes time to look at glue, you think you can save a buck. And you do save a buck, and in doing so, doom your design to failure. All right, I would like to see if I can't get this connector apart carefully, and maybe I can save that HDMI controller board. Okay, so we've got a... I should zoom out here. You're probably staring at nothing in there. Sorry about that. So what I'm doing right now is looking at the actual LCD controller itself. So, I mean, the other thing that we had was just a logic board. You know, it'll take your input and, you know, do whatever it's going to do to it. Maybe do some rescaling and whatnot. And then it sends it to this board, whose job is to run all the pixels. And since this board is designed specifically for this panel, you know, let's say you put in 1080i or 1080p or 4K video, whatever it's going to be. I mean, that doesn't change the number of pixels that are going to be on this display. It's going to have a fixed amount. So by the time it gets over to this board, this little one down here, this is going to be purpose-built for this panel, or at least this resolution. Okay, so these are loose grounding tabs. That's something interesting to look at. So to make the ground connection, let's even go a little tighter. To make the ground connection here complete, these tabs are just spring-loaded flex fits to this. It's kind of interesting. Interesting. And let's see if we can't give you guys a little more light. Not much. All right, so what is holding us together? There is the liberal application of tape. And it might just be that. Everything about this screams well-built quality. I mean, the tapes are cut to precise lengths. It seems like the fabricators of this board really went out of their way to do a good job. Everything's put together. It's clean. The boards look like they've been cleaned. We'll know more in a minute. It's all Rojas. Yeah, that glue's coming apart in my hands already. I already got into some of the stuff that leaked out. Okay, well, I'm going to have to be a little ginger with it. You know, oftentimes when designers have to work with these things, you know, before they have a board in hand to play with, they have to play with FPGAs first and set up an FPGA to do all of their work for them. Okay, that's loose. And then they can use that to create the ASICs that they use to drive their board if they indeed need an ASIC and can't get an off-the-shelf part. So now I need some different tools. And today would have been a great day to wear gloves, but yeah. When I looked at a board that had obvious glue issues, I didn't think that far ahead. Huh. Goes back to me being the reason I can't have nice things. All right. Let's see if we can't encourage this screen to come loose. And wow, that just popped right out. And that glue is a mess. Yuck, yuck, yuck. Okay, so that cracking is me from the prying. This is a very thin board. There's oil that is used to create a gapless connection between the screen, and this LCD, so the touch screen and this. And then I am going to pull this off because I am sick of playing in that glue. So that is icky, and it is going into the trash for the time being. Now we've also got the we've got a free-floating polarizing filter. I said that you don't often, you do sometimes get those, not always, but in this case we did recover that. So I'm gonna hold on to that, and we'll see if we can't come up with a project for it, or at least see if we can't give it a second life. And the touch screen we're going to leave alone for now. Okay. Everything is covered in that adhesive, and that adhesive is, it feels like it's not even cured. It's just stickiness and ickiness. So, like I said, it's really a shame that everything else in this looks so clean and so well put together that that's just a materials problem. As an electronics engineer, I don't even know what you do about that. You have to trust your suppliers. You have to, I mean, we're not glue experts. We're hopefully not expected to be glue experts. But a customer is going to look at that product and they're going to think the whole thing's crap because visibly the, it looks like crap. But from what I'm seeing with everything else, nothing could be further from the truth. So that's, I mean, man, that just sucks. I don't want to say it's bad luck because at the end of the day, it is somebody's responsibility to figure stuff out. But, man, what do you do? I don't know. That's rough. Okay, but we've got boards to look. Gosh. You probably can't tell, but everything that touched that glue is now stringy and icky. I'm gonna have to clean everything. But that gave us 4 boards to look at. We're gonna start with the simplest and work our way up. After we do a little bit more damage with that adhesive. Well, man, I am really sorry there, Arduino, that happened to you. Really sorry. All right. How we doing out there in TV land? You guys still hanging out with me? Feel free as we go through, if you have any questions, to ask them in the live chat. It seems that we've got, based on what I'm seeing on my screen, we've got far more viewers than we do people talking. So, I mean, join right in. All right, let's tighten up. The first board, and perhaps the simplest one, is this little multi-button control panel. And on the button, you've got these machined aluminum user interfaces. So each one of these is a momentary switch. There's underneath these little, and maybe we'll take one apart here in a minute, but you've got these little pieces of spring metal, and you push them down and they create a connection. Now, since these things are pretty small and you know you'd have trouble with users touching those, the designers made these aluminum caps. I can't get them to stay on. Sorry about that. And these things are pretty, I mean, these are solid. Somebody had to, you know, set up a mill program and just go through and machine out a ton of those just to give this a little more substantial feeling. That's crazy to me. I love it. And it looks like we've got just those 5 switches, a connector, and I can't tell yet. We'll pull out the microscope in a moment. I can't tell if those are resistors or caps, or maybe it's a resistor and a capacitor. And then they just ran this. They made a 2-sided PCB. They didn't have to. I mean, this is making me sadder and sadder as we go through this, that this little screen failed because of glue. And it's glue that I still have stuck on me. These guys, they seem to have built a really good board, and one part failed, and that's what got them. Okay, so our microscope view is on channel 5. Let's see if we can't figure out how to get this thing in focus, huh? Okay, we are really zoomed in. This is one of those buttons. And we've got a piece of plastic. Which one of these am I hitting? This one. That underneath is going to have a piece of it's going to be a little bubble of spring steel. And then here are where are our 2 little components. You know, I think I could do with a little less zoom. This is our FFC connector. So there's that little piece of plastic similar to the one I ripped off earlier that will keep everything pressed fit in there. And I think the problem is my camera's upside down. I think that's what's getting me. Okay, so these are LEDs. And you can make out how these are connected. Each one of these little guys has, you know, you can make out the bonding wires that go to the lead frame. I can't really tell which one is the anode and which one's the cathode from here. But you've got that little doped silicone that when you run electrons across it, it lights up. So those are tiny little guys. And you can even kind of sort of make out the silkscreen courtyards. See how they're kind of bubbled up there from the surface? Interesting. So they ran a trace out to everything. They did the traces for the buttons on the back side, and here you see some ground return vias. This is just tying the these vias just tie the ground pores, the copper pores together. Almost like there's a little bit of bubbling on that one. Wonder if that's LPI, that the tinting that just went in. They did tint their vias, which is great to help keep contaminants out. Sometimes you do have troubles during reflow that if there's stuff captured inside, the via will pop, it'll bubble, it'll explode. And these lines and striations that I'm seeing here just lets me know that they did not really wash this board. They probably just went with no clean. Flux might be the stuff that I'm seeing. Or, you know, something I could be wrong. It could be that I'm seeing evidence of the adhesive left behind. Maybe they did go to the trouble of cleaning it and I just can't tell because of all that adhesive stuff that I'm still sticking to. This is interesting. You can make out the so the way that a via is formed, you drill a hole in a board and then you electroplate and you build everything up, and then once everything's built up, you etch away copper and you create the anti-pads and the space between the traces and all that. And you can kind of make that out here where it's such a high magnification, you can almost make out the 3D effects of this. One of the things I would have liked to see, it's not that big a deal, but it would have been nice to have seen teardrops, and it would be nice to see larger pads, just because that will increase your overall yield. So they just went ahead and ran a net for each and every switch. That is the nicer way to do things. So on the bottom side of that is where our FFC connector comes. And then you will see, we are at a very high zoom level right now, but you will see at the edges that these guys did vias every, oh, I don't know, let's call it 2 to 3 millimeters, just to stitch the copper layers together, the copper pores together, so that you don't end up with unintentional radiators. And then one thing I don't like is these mounting screw holes. They did not leave a whole lot of material for a hole that big. It would have been very easy to break out the edge of that board. And I don't know that there was really any need for it. They could have simply added more material. So that would be something that I would recommend. Remember, just because you can make one of something doesn't mean that you can manufacture something. It's very easy to have low yields or have suboptimal yields. Let's say you've got a really good yield. Let's call it 90% yield. Well, if you're making 100,000 boards and you're only able to save 90,000 of them, that's 10,000 boards you're putting in the trash. That's not so good. So I do like that they kept the copper away from the edges. That's important. You can see that we don't have very clean route paths around all sides of this. And that's pretty typical, right? Things move, especially small things move. This feels like, I would produce this board. The only comment that I have would be there's really no reason to have that little material around the edges. Use more material if you can. And they had room in the board. So there's the first board. That is our switch assembly. And gosh, man, everything. I am sticking to my workbench right now. I don't like this. Okay, let's go back overhead. We'll zoom out a little. Our next board came from part of the was this LCD or was this? No, this was the resistive touchpad assembly, and it is covered in adhesive. You can, all that stuff there, that's adhesive from the screen. So we're going to go back to microscopic view and take a look at that. And if you don't mind me for just a moment, I am going to rotate my camera so it's easier for me to gain. Oh, it's moving in there. I don't want that. Stop moving. Okay. That'll be a little easier for me to orient things. And let's zoom out. I'm using a little Amscope trinocular microscope here that I really like, with the exception that the zoom really throws off the focal plane, so you've got to change it all the time. And I just removed a bit of polyimide that was covering the backside of this board and protecting this from something. So the first thing we've got is a QFN package, a quad flat pack, no lead. And this looks like it just got soldered right onto the edge of the board. I don't recognize the manufacturer markings. So something from offshore, something not used. Looks like we've got a little bit of not super glue, but hot glue. Nope, more adhesive. I lied. Gosh, this adhesive, man. And it looks like the designer had plenty of room, just ran some nice leisurely traces. I mean, these are probably 3 to 4 mil copper. He kept everything clear of the courtyards, but kept everything really, really close. This is a tight design. Ran curved traces, probably just for aesthetics. But I do kind of like the looks of this. So he brought in 2 caps. I assume one's decoupling for the purpose of decoupling and the other's for the purposes of bulk, like a 0.1 and then a slightly larger one, you know, 0.1 microfarad. And then that is pulled out to what appears to be a filled via, or perhaps just a micro via right there. And these are pretty small traces. This is all, you know, 3 mil trace in space. Looks like we've got vias around the edges on the copper pores, again, just to help prevent this bit of copper from becoming a big fat antenna. Vias broken out. I don't know why they're offset like that, but we might figure out on the other side of the board. So one of the interesting things, you know, the reason that you see right angle traces is because the early EDA programs, that's really all they could do. But nowadays, you're not limited by that. You know, if you go back before we had computer software laying out traces, they were all over the place. You know, they straight line connections from one thing to another at like a 13.3 degree angle. Or it takes a curve that has really no defined radius, and that's because people were laying these things out with tape by hand, and it was fine. So this designer, you know, I mean, I don't know what software they're using, and nothing is speaking to me here, but you've got kind of the same feeling. There's nothing really programmatic about those traces. I mean, it very well could be that they have software laid out and they just had the curve stuff turned on, and they included some additional angles like 45 and 30 and whatnot, and it snapped to it. Or they could have just turned off the snapping altogether and just drawn a couple of these like I was looking at that trace there. You know, maybe they drew it by hand. I doubt it. They probably just have some rules that lets it follow additional angles. I know Altium lets you set that up. I don't know what other software does because I don't use every software that's known to man. Here is something I like to see. They used multiple vias, tying this back to the other layer. I don't know what that is. It's interesting. Is it just tape? Maybe I'm just looking. No, it's really thin if it's tape. I don't know what that is. It looks like it's a weaved pattern of something. Huh, I don't know. It probably just really thin tape, maybe. So, weird thing though, we've got filled vias here and unfilled there. Usually if you're going to fill vias, you fill vias. But maybe these are micro vias. Maybe there's an intermediate layer. I wonder if we can tell. Enhance. Well, I can see our two outer layers clearly enough. But maybe you guys can tell on the camera. I'm looking through the microscope and my eyes are just being blinded by the light. I don't know. There could be some intermediate layers in there. It kind of looks like there are. There's another 1, 2. Like this is a really thin 4-layer board. This is thinner than a typical PCB, by the way. All right, so let's get cracking on the other side here. The board is protected by some tape. That I am removing in the way viewers love, just mark smash style. There we go. And we'll get back into focus here for you. So this was covered in tape. That's why there's so much debris on it. And this is just a really tiny test pin or programming setup. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pins. So that's enough, you know, for JTAG. So I'm thinking more that these are micro vias, and the other ones are through holes. So micro vias are forced to have a 1-to-1 aspect ratio. They can only go down usually to the next layer. Sometimes you can go 2 layers, but usually you can only go down 1 layer. That must be what we're looking at, just HDI design. So they used these to program, and then they staggered them just to make it easier to make a jig. Because if you put these things all side by side, it would be a pain in the butt to have something mechanically that could hold all those pins without shorting. So you just space them out. More micro vias in that little connection there next to where it says 5V. And then more programming test points. More glue. Yuck. This is really just a miserably sticky thing to play with. So micro vias on this header that are staggered just to make everything fit. Our cat Chester says hello. We've got a clock, little crystal oscillator there. So nothing really too... This is a really narrow board. You know, it's only, I don't know, 3/8 of an inch wide. That has its own challenges when you are manufacturing and jigging this thing for assembly work. Sometimes you'll have a carrier board outside of it. I mean, I've got nothing negative to say about this stuff. It all looks really clean. That stuff that I thought was tape is tape. It peels back with the good old thumbnail rub, and there's some information hiding on the back. Looks just like component locations and descriptions. But again, everything seems really clean about this design. It's just that adhesive that got them. Such a shame. Okay, I am getting more time for more wipes because this stuff is just getting all over. It's really quite a pain. All right. Now for the LCD panel controller. So LCD panels they handle a lot of data. I mean, it adds up really fast. So even if you take a 640 by a 480, right, 640 pixels across by 480 pixels tall, and you multiply that, you know, that gives you the number of data that you need, or the number of pixels that you have. Then you multiply by 3 pixels. Then you multiply by your color depth, you know, 8-bit, 10-bit, whatever it is that you're running on. Then you multiply by the frames per second, you know, 30 or 60. Then, you know, it adds up really, really fast. Now, we don't do a lot of 640 by 480 anymore. Everything is, you know, 4K, and the movement is towards 8K. It's an unimaginable amount of data that has to be processed with every frame refresh. It's crazy, crazy, crazy. So with that, let's take a look at what runs our LCD. And that is this board right here. Long and thin. Everything on this is tiny, tiny, tiny. Even with the inductors, you know, the maximum height of this thing is probably on the order of like 1.6 millimeters. There's not much to it. Let's see. Thickest part is, nope, I lied. It's a little bigger than I thought. With the inductors, the tallest parts is about 2 millimeters. We're about 1.8 on the ICs, so it's a little thicker than I thought. But I don't have a metric calibrated eyeball, so I'm going to give myself a pass on that. Okay. Slightly de-stickified. I know I've got at least one viewer, the kitty cat Chester over here to my right. What we're going to do is start over on the right side and work our way to the left. And we've got top and bottom. On the bottom side, it is just connectors. There's no components. So I probably will start there and work my way over. But one of the things to remember, especially when you're dealing with these thin boards, is that putting components on both sides is really going to increase your expense, right? This has got to go through the reflow oven. If it goes through once, the parts are going to stay on, no big deal. But if it goes on that second time, this part can flex and move. The parts on the bottom can pop off. The parts on the top, while the parts on the top stay. You can have increased stresses on your larger components, like this guy. If you happen to have two of those on either side, it can really stress the board. And as things heat and cool over the lifespan of the product, you can end up cracking the solder joints on your ICs, releasing things. So let's start over here and work our way back. Funny thing, I scheduled Mark Voids a Warranty for noon, and I screwed up time zones. So I figured I would just do 2 Mark Voids a Warranties today, one at 11 and one at noon. And what I ended up doing is picking a project that is so involved that I'm going to run over into noon. So lucky viewers. All right, we've got a board with radiused edges, and you can tell that they did the copper to the copper pores to follow that radius. But here, where they had the copper held back by a certain amount, they must not have had the same rules with their vias. So these are through-hole vias, and for a through-hole via, and I don't really know what size this thing is, but I'm going to guess somewhere in the order of 6 mils, but I don't really know. Well, you need a via pad. That's the amount of copper that is around the edge of that hole. And the via pad is, there are manufacturing minimums for those. Your manufacturer might want an additional 4 mil annular ring. Well, the rules for their copper pore and the rules for their pad annular ring size must be different, because you can see that the copper edge to board edge spacing is encroached on there, which is something that you don't often want to do. As you can tell, these boards don't always get routed, they don't always break cleanly, and you don't want to inadvertently get a short circuit. So that is something that should be flagged by a DFM, but maybe it just got missed, or maybe they just said, forget it, let's go with it. So we've got quite a few through-hole vias that we're seeing here, tying copper together. Unless you're dealing with very high frequency or very fast edge rates, you could do the copper pore stitching, say every 100 mils on center. That's 2.54 millimeters for those of you across the pond. Not that it matters in the least little bit, but aesthetically, I just like rounded corners instead of mitered. So nothing too exciting here. We just have the connector broken out immediately into vias, and for the what I assume are the power plane, I wonder where the ground is. For what I assume is the power plane, they used multiple vias. That's always an excellent idea. You never know when a via is going to fail on you, especially if you're dealing with high current. So then, where do we tie to ground? I don't know. More of that nasty adhesive. Yuck, yuck, yuck. So I do believe they cleaned these boards and that adhesive just came in and got to it. Here you've got some vias that aren't tied to anything, and the reason that you have that is they're coming from other layers, and through-hole vias are always cheaper to make than any other kind of via. So they just made some anti-pads around those, but those make connections on other layers. Same issue here. I would have liked to see some more vias tying these copper bits together, because at high speeds all of this copper can end up being a big fat antenna. As Dr. Eric Bogatin says, there are two types of electrical engineers: those that design antennas and those that don't know they design antennas. Right? We are all antenna designers if we're not careful. So let's see if we can't back off of this and get an edge view. Sorry about all the motion. Hopefully not making you out there too sick. So I was looking at the solder fillet and I was trying to get an edge view. And I don't know how good that is or how much you can tolerate that. But IPC Class 3 requires that solder go at least 1/4 of the way up the vertical pad height, and I just wasn't seeing that there. But I don't think I can demonstrate it, so we're going to have to move on. I'm also seeing some so here's one of our ICs, and I can't really make out the top side marking, so I don't know if that's anything we know about. Here we're seeing multiple vias tying a copper pour together. Anytime that you can get away with that, you should do that. I haven't seen any differential pairs traces that we would know would be high speed, so I don't know how these guys handle their vertical returns. This is an inductor, huge at this magnification. You can also make out on the solder, you know, some of the individual metallic crystals. For solder to create a electrical and mechanical connection, you've got to form these intermetallic crystals, and you know, those are mixtures of tin and copper. Used to be, you know, you'd have lead, but we don't do that anymore. So here we've got a little J lead part, or J leg, J lead. So nothing too exciting here. We're just looking at things in close up. But the designers, I mean, they did a good job. Assembly did a good job. They cleaned the boards. I would have liked, other than wanting to see a few more of these types of vias in the copper pours, I've got really nothing to say about any of this board. I mean, it's all a good job. So let's back off and move over to the logic board, the board you've all been waiting for. Okay, this is our board by Kevin. And on first appearances, which you may or may not be able to see, we do have our first clean board. Now, that being said, everything that I've touched in the last hour has been covered in this nasty glue. So if you do see some schmutz on this as we go through, that's probably not the fault of the assembly house. We do have some great design techniques here. You've got, again, parts only on one side. That really does cut costs down. You can see on the back side, or it's what you don't see that's interesting. There's no silkscreen layer. That saves money, right? Silk screening is a process. If you don't need it, don't use it. They didn't need it. They did get their logo and all of that in a copper pour by removing the solder mask layer, and this thing went through a hassle process, hot air surface level. So they still got information back there. They still got a logo. It's just with that. Now, there's also some what appear to be thieving pads, but not copper thieving pads, because there's a copper pour across this entire bottom. This just looks like solder thieving pads. Something, I mean, there could be a hidden use for those that I'm not aware of, but it looks like they just use those to, well, no, they used them on the front too. Is it thermal? No, I don't think so. I think that is just for when this thing goes through reflow, just to kind of keep heat. Maybe it's to keep the heat level, to keep this board from warping during reflow. I don't know. One thing I will like to look out when we have the microscope out is there's a hole in the middle of that thermal pad, and I'd like to take a look at that thermal pad too. But other than that, we just have a clean looking board. All right, Kevin, let's see what we got. I have confidence in you, Kev. I have confidence in you. We are back on microscope view, and I think for this board we are going to zoom out a bit. Over on the right hand side we have an unpopulated battery header that I'm looking for on our microscope. Is this it? Yeah, so there's a battery in. So it looks like this thing was designed to have a charger circuit and you know, be able to work remotely, which is kind of cool. So good job, Kev. And down from there, through this metallic pad, we start entering our power circuit. So this is our, he's got a switcher circuit designed in here, it looks like, and a bunch of through holes that are tying that entire copper pour to an adjacent layer. The reason that you want to do something like that is to prevent this area from becoming an antenna. Kevin knew that, and Kevin took steps to mitigate the possibility. We've got some integrated circuit. I don't know what those striations are on those J leads. That's interesting. Looks like the silk screen might have come out of a... Actually, gosh, I don't know. That looks weird. Is that a... That can't be a printer? Just a lousy mesh? I don't know. The silk screen looks odd to my eye. I don't really know what caused that. And we've got what appear to be some solder thieving pads. Solder thieving is different than copper thieving. In copper thieving, you're trying to ensure the integrity of the electroplating process, making sure that everything goes relatively evenly. Solder thieving, you're trying to make sure the solder, the heat's distributed evenly, or you know, you don't, sometimes you'll use them to steal solder away from a pad so you don't get a short circuit. So Kevin just did some good stuff. We've got multiple vias tying everything together. It looks like there's all through hole. I haven't seen anything that looks like it's a micro via yet, so that keeps costs down. We also saw that he didn't use silkscreen on the bottom side. Another cost-saving thing. This is how you know when you have an experienced designer. Now, this piece of copper here with all these stitching, it looks like he designed a via fence. So he was worried about energy from the switcher part of the circuit coming over to the logic side of the circuit. And he was really worried about that copper becoming an antenna down here because those things get tighter together. So here we've got 5 volts output. So that's just a little micro USB. We've got our 12 volt input, and to save space, this particular device is cut right into the edge of the board. I can show that to you on a long view. And everywhere he could, you know, you've got vias tying everything together. Bravo, Kevin. Bravo. Let's cruise down and let's start looking at how he did his digitals. HDMI is a series of differential pair signals, and here you can make each of those out. So these are grounded on either side of the differential pair. We've got some unused. In addition to the digital data that gets transmitted through, there's other signals that allow bidirectional communication. You can figure out what your resolution is. You can sometimes do networking. So these differential pairs are straight shots. He did not interrupt these for anything. And it looks like he gave himself some cheat pads. I'm guessing these are cheaters. So every now and again when you do a design and you're not quite sure if you need terminating resistors or not, you're not quite sure if you wired everything up correctly, you can give yourself some cut traces that you can interrupt and do some rejiggering if you need to. And it looks like that's what he did. And he ended up not needing them. And I'm guessing the reason that you've got these traces that are just slivers, which by the way would throw a DFM error, is probably their grounds, and he used those so he could tie in a capacitor or a resistor if he needed to, and he just ended up not needing them. I really like Kevin. So here's something that's kind of interesting. If we look at this via that's centered on the screen, you can tell that the via is not perfectly centered. They're never perfectly centered. They always wander one direction or another. And if you teardrop, if you keyhole, you can save traces that would otherwise be lost if the drill wanders in the direction of the trace, like this one did. For a class 3 device, you need a minimum of 2 mils exterior annular ring or 1 mil interior, and we might not have that there. Remember, the name of the game's increasing yield. It's not can you make a board, it's can you make a bunch of these without having expert machine operators walk your board through every step of the process. Here we've got a stitching via, you know, one that connects this copper pore to the copper pore on the next adjacent layer, and looks like he could have moved these in a little bit and not lost anything because he was encroaching on his trace and space minimums there. you know, these are just clean boards. We do have some trace slivers here that could become antennas. I'm following this trace. This is a long trace. So we've got triple via termination. I like it. I like it. As you can tell here, though, we're kind of wandered off to the side. I would imagine on the other side of this board, the trace continues in that direction somewhat. I would hope so. But if he had spread this out sideways a little bit, I think he would have been in a better position, especially with vias that large compared to the trace size. But here's what I'm looking at. So I'm going back down here, and I'm going to follow this trace back way over here. That is a long trace, and that looks like a LDO to me. I could be wrong, but I'm guessing that's a low dropout linear regulator. That is just a long run, and it goes next to, I don't know what it goes next to. I don't know if that's digital or just a signal line or what. Yeah, I don't know what that is. I like that. That's good. It'd be kind of nice to know what was on the other side of that. Let's see if we can figure it out. Okay, so let's, I think I found it. I'm looking for those triple vias. Okay, so those triple vias come out here. And again, had he kind of gone diagonal a little bit with those, maybe set them off at like 15 degrees, there'd be more copper. But I love that he did a triple via stitch. Oh, and then we're going back now to the other side. I don't know where it goes from there. It could be hiding underneath the connector. I don't have this stuff indexed well enough. It's probably under the connector. Okay, as far as connector tying together, two different strategies here. If we look, you've got 4 individual traces tagging the connector, and then it goes into a big via trace, and that's okay. It's really nothing wrong with that. But I kind of prefer this style myself, where you tie them all together, big fat copper pores. I would probably, I don't know. It would depend on the pitch of this particular connector and which one I would choose. But I tend to like more copper, the better. One thing I don't like, and I don't know what's going on here, is why we have this copper sliver. You've got all those pins tied together and they go nowhere. I don't know what's going on with that. It could be that whatever's happening with it is happening underneath the connector. In fact, that could be where our 3 vias went, that power trace. That would make sense to me. But then why would you have the copper pore on this side? I don't know. I would have liked to have seen teardrops because, again, vias can wander. And if you can have larger annular rings, do larger annular rings. But Kevin, you have my respect, man. This is a looks like we've got a well laid out board. If we come back to our overhead view, I'm going to spend a week decontaminating my workspace from this glue. We've got over on the right hand side the power. We've got a no man's land where he's just trying to give some space to keep the digital signals separated from the analog ones. So you've got your 12 volt, your big switcher, 12 volts over here. Individual, so I'm guessing these are lower voltage networks. You know, probably 3.3, maybe 1.8, 1.2. And then from there, Actually, you know, I think I can get a little closer up for you. There we go. So we've got our 12-volt section over here. You know, he tried to build a via fence and put in some no man's land to keep the signals on that side of the board. Over here, we go a little bit more, and you've got other switching circuits and resistors and whatnot. And then we get over into the digital. And I mean, just look at how cleanly everything looks. Everywhere there's a copper pour, you know, you've got stitching vias. I like it. I like it. I like it. Well, Arduino. I don't know what to tell you. This looks to me to be absolutely very well designed and laid out. Let me cancel that for a second. It looks like it's all very well designed and laid out. And you just bought some bad glue. And your reputation's going to probably suffer for that. And that's a shame, because everything you did seems to be top-notch, top-rate, top quality. So I'm sorry. I wish I had some advice on how to solve that problem. But with that, we have just finished yet another Mark Voids a Warranty. I know, guys. I know. It's been fun. I've got another board to nail. Actually, you know, this one, with the exception of that FFC cable that broke, and I think I can probably steal that little pressure part off another board. But with the exception of that, this is a good board. I mean, I might be able to conceivably use that to control some other LCD somewhere else in my shop. I don't know yet. But Arduino, you guys did a good job. Kevin, props to you, my friend. Props to you. All right, that's it for Mark Voids a Warranty. We've got another one scheduled for next week at this time. We've got all sorts of fun stuff we can take apart. We've got machine vision cameras we can look at. I have in the other room a lens system that is so large it's difficult for me to lift by myself. It's off an old television camera. I picked it up at a scrapyard. But before I can take that one apart, we need at least 500 subscribers, and we are already almost there. We're almost at 400. We've been gaining, you know, 2 or 3 a day. So tell your friends, tell your neighbors, tell your friends' neighbors, tell your neighbors' friends to join, subscribe to Mark Voids a Warranty. And I'm going to try to keep improving the production quality each week. I just added, although just this past week, but I haven't had a chance to learn how to use it, a Blackmagic Design, what's it called? HyperDeck Mini. So this thing can play back video. So when I'm talking about things like vias, at some point I'm going to be able to press a button and have an image come up on the screen live that you guys can watch. If you need any board design work, or you have any questions, or you want to do anything, visit us at aapcb.com. And with that, that's it for this time. We'll see you next time on Mark Voids a Warranty.